Welcome everybody, this is Conrad Diaz from the Cognetics Mechanical Engineering Academy. In this video we talk about how to specify screw threads on engineering drawings based on the Unified Inch Screw Thread Standard. Let's get to it. Let's talk about the scope of this video module. What we're going to cover is Unified Inch Screw Threads and relevant standards, how to specify thread callouts on engineering drawings. We'll talk about coarse, fine, extra fine threads along with their class fits, and of course internal and external threads. What we do not cover in this video, but we plan to cover in other Academy videos, is how to choose screw and fastener types and sizes, how to choose the length or depth of thread engagement. We have other videos also where we'll be talking about metric threads, pipe threads, and other types of screws, such as self-tapping screws. Okay, so the main standards that are relevant to this topic are listed on this table. Let's talk briefly about ANSI and ASME. ANSI is the American National Standards Institute, and it is a privately funded entity which happens to be the United States member of the International Organization for Standardization, ISO. ANSI itself does not write standards, but it does approve them. ASME is the American Society of Mechanical Engineers, which is an independent, not-for-profit organization. ASME is a well-respected standards development organization. So the way it works is that ASME develops and publishes standards while ANSI approves them. That's how they are closely related. So there are 4 standards on this table. The first one, ANSI ASME B1.1, of course, talks about the Unified Inch Screw Thread Standard. The next one, B1.7M, has to do with definitions, letters, and symbols associated with the threading standard. Next, we have B1.3M. That one talks about how to measure the threads to make sure that they are acceptable and conforming to the standard. And of course, we have the very popular Y14.5 that has to do with dimensioning and tolerancing on engineering drawings and related documentation. All right, so when we get to the point that we have engineering drawings and our designs include threaded features, we need to define them on the drawings. These specifications are typically called callouts. So we have a threaded feature callout, and it, per the standard, needs to come with the following information: the size of the thread, the pitch, which is the threads per inch, the thread standard and series that it adheres to, the thread's fit class, which is sometimes omitted, the minimum depth or length of the thread, depending on are we talking about an internal thread or an external thread, the number of instances of the threaded feature, and what is sometimes omitted as well, and we'll talk about this later on in this video, is the pilot hole diameter or drill size along with its depth. So let's get into how to specify a threaded feature per the Unified Screw Thread Standard. We see the format of the callout here on the screen. Let's go from left to right. First, you see the screw size or nominal diameter, followed by a dash, then threads per inch, space, followed by the thread form and series, dash, class fit, another space, and then we have the depth dimension, space of course, and the depth abbreviation or depth symbol. In the case of a thread that goes all the way through a part or a wall, you would not have a depth symbol, you would simply say through. Underneath we see the number of instances as applicable. So let's talk about each one of these in more detail. First, let's talk about the size of the thread and its pitch. The table that we see here on the left is a partial list of some commonly used nominal screw sizes. And these can vary by industry, but this list is pretty good to start with. On the left, we have the sizes of the screws, so the size number of the screws. And on the right, we have the basic major diameter in inches of the screw thread. Looking at the left column, notice that some of the numbers are listed in parentheses. These are listed in parentheses because they are available, but they are not commonly used. So it's always best to stick to items and components that are more commonly used. Okay, so looking at number 8, for example, screw size number 8, its major diameter would be 0.164 or 164 thousandths of an inch. Let's see. You can see also that sometimes the number is not listed, but rather a fraction. So a quarter right there, a quarter size screw is very commonly used. And of course, it represents a quarter of an inch, which is 0.25 or 250 thousandths of an inch. Okay, now the pitch, looking on the right side, as we know, is the threads per inch. That table is also a partial list. It's probably not legible to you, but it lists commonly used threads per the standard. We'll talk about this in a little bit more detail because thread pitches correspond to specific screw sizes, okay, as outlined in the Unified Inch Screw Thread Standard. But looking at, let's say, 14, which is not, as I said, not very legible to you perhaps, but 14 corresponds to 14 threads per inch, which its spacing between from thread to thread would be about 71 thousandths of an inch. All right. Looking at the callout format once again, so far we've covered the left side, which involves the screw size and its pitch. Next, we have the thread form and series along with the class fit. Let's talk about the thread form and series first, and then we'll talk about class fit. So the commonly used thread forms and series are the Unified Coarse and the Unified Fine series. There are many others, but these are the two main ones. Briefly, let's discuss when you would choose one or the other. Unified Coarse thread is commonly used, it's general purpose, and tends to be used in lower tensile strength materials such as aluminum and many others that are lower in tensile strength. There is less of a risk of cross-threading or stripping these threads because their pitch is smaller. Each thread is spaced apart more from the next one. So less risk of cross-threading or stripping of the threads. On the other hand, the Unified Fine threads are higher pitch for the same size of a screw. These are, for example, in the case of external threads, are slightly stronger in tension than the equivalent coarse threads for the same size of screw. That's because the tensile stress area is slightly larger in the Unified Fine thread than in the Unified Coarse thread for the same screw size. Also, the Unified Fine thread can provide fine adjustment a little bit better than the coarse thread. And there is a slightly higher risk of cross-threading, but depending on the application, you need to choose whatever works best. And we do have another video coming up from the Academy that will address how to specify screw types, their threaded engagement, the thread form and series, etc. So please look for that at mechanicalengineeringacademy.com. The table that we see on the right, as mentioned before, you cannot simply choose a pitch at random and match it up to a screw size. There are diameter pitch combinations that are a part of the unified standard. So this list shows some of them. Looking at, let's say, number 6, we have a number 6 screw, which we already know that is its major basic diameter is 0.138 or 138 thousandths of an inch. It's not too important once you get used to specifying screw sizes. Sometimes you get to memorize their major diameters, but it's not essential. By experience, you'll be able to choose the proper size of a screw without thinking too much about it. But so let's go back to number 6. It's if you are designing a threaded feature that has a number 6 thread and you want coarse threads, you would choose 32. So your callout would say number 6-32. On the other hand, if you need fine threads, you would say number 6-40, 40 threads per inch. Okay, and not typically used, but depending on the application, if you need finer adjustment, even beyond what the UNF Unified Fine Thread Standard can offer, there is the extra fine standard, UNEF. For example, a quarter size screw. A coarse thread would be a quarter 20. Fine thread would be a quarter 28. Extra fine would be quarter 32. After the thread form and series comes a dash followed by the thread class fit. There are 3 major class fits in the Unified Screw Thread Standard. That would be Class 1, Class 2, and Class 3. Class 1 is loose fit. Class 2 is the most popular in use, and it is standard fit. Class 3 is a tight fit. After the class is defined, we have a postscript, either an A or a B, with the A being for an external thread and the B for an internal thread. So for external threads, we end up with the class fits 1A, 2A, or 3A. And for internal threads, the class fits would be 1B, 2B, or 3B. All right, we're making good progress here. Let's go ahead and look at some examples and variations of internal thread callouts. On the table here, looking at the left side, the first column, we have screw size or nominal diameter. On the first row, we have the number symbol followed by a 6. So that would be a number 6 screw thread. Second row, the number symbol is omitted. On the third row, we have the basic major diameter of the thread called out, which in this case is a 0.138, 138 thousandths, which corresponds to a number 6 screw. Word of caution here is that if you use the basic major diameters, not everyone knows them by memory. So it is going to be a little bit harder. Some people are going to have to go to some chart or lookup table and figure out what screw size they're working with because you listed the major diameter instead of the number itself. The other thing is potential error here that should really not happen, but 0.138 in this case has 3 decimal places. That does not mean that the machinists or the fabricators are going to go to looking at the tolerance block and the title block and see that 3 decimal places corresponds to, for example, plus minus 5 thousandths of an inch. That is not how it is to be interpreted. Because remember, this is the basic major diameter according to the unified standard. So 0.138 simply refers to a number 6 screw without tolerance associated that is related to the tolerance in the title block. So my recommendation would be to use the actual screw numbers. On the fourth row, we see sometimes there are no screw numbers, but we can use their fractional size. This would be a 1/4 inch nominal size screw. We have examples of threads per inch, the pitch. So we have a number 632, a 640, a 640, and a 1/4 20. We already discussed the thread form and series. We have some examples of UNC and UNF. Class fit, since we're talking about internal threads, they are all a number followed by the letter B, which corresponds to an internal thread, 2B, 3B, and 1B. The length or depth, well, in this case, we're talking about internal threads, so it would be the depth of the thread. On the first row, we have 0.13. On the second row, we have 0.125. They're about the same, but in this particular case, 0.125 could represent plus minus 5 thousandths of an inch, for example, if that's what the title block says, the tolerance block on the title block. 0.13 would correspond to 2 decimal places. So the tolerance is looser, a little bit easier to generate, and a little bit cheaper. So as far as depths and lengths of threads, typically 2 decimal places are used. On the third row, we have a 1/4 of an inch deep thread. And on the fourth row, an example of an internal thread that goes all the way through the part or through the wall. So no dimension is called out, you simply spell out the word through. On the last column, we have the depth abbreviation or symbol. So deep is sometimes abbreviated as DP. Quite often now, especially with the modern CAD programs that we use, the depth symbol is used. It's often automatically placed in there by the software. Or you can go ahead and spell out the full word deep. Okay, and fourth row you see, since that particular example is a thread that goes all the way through, there's no symbol to go with that. Okay, on the lower left, if we were to read these examples all the way through, we have a number 632 unified coarse class 2 fit thread, which is 0.13 deep. The next line is 640 screw, 640 thread, unified fine thread, class fit 2, it's internal, with a depth of 0.125 inches. Third row is also a number 6 screw with a pitch of 40, unified fine thread. This is a little bit looser of a fit. Tighter of a fit. It's a class 3 internal thread, which is a 1/4 of an inch deep. And the last example, 1/4 thread, unified coarse, class 1. This one happens to be looser, as an example, internal thread, and it goes all the way through a wall or a part. Looking on the lower right, the image in the middle, you see that there's also a pilot hole dimension called out above the thread specification. Word of caution: if the pilot holes are called out in your company, or that is your practice, know that there are dimensional tolerances associated with those dimensions per the title block, tolerance block. Word of caution is that pilot holes are usually not called out because the thread is fully defined by the unified standard, simply by calling it size, pitch, class, fit, etc. If it is called out, the pilot hole, it could be because you have a manifold application and you need to make sure that the pilot hole, which acts as a fluid path, that you have a controlled diameter for that. Or perhaps your company or industry practices demand that the pilot hole be called out on the spec. Okay, to be thorough, here are a couple of examples and variations of external thread callouts. Let's focus on the 2 images at the bottom. The one on the left, we have a number 632 thread, unified coarse, with a class fit of 2 and A because it is an external thread. Now, there's no depth associated with an external thread, but rather a length. So in this particular callout, the length of the thread is expressed as an actual dimension, in this case being 0.20. The thread on the right side is pretty much the same thing, but expressed a little bit differently. It's a number 632 UNC2A thread by 0.20 in length. In this case, the X represents by a particular length. Not to be confused when it's used elsewhere, as we will see a little bit later in this video. You could say 3x, for example, which would represent 3 instances of a thread or of a feature. It would be the number of instances followed by an x. In this case, that is not what we're talking about. We have an x and then a length. So it's interpreted as this thread by 0.20 in length. So we're done with the majority of the thread specification. What we have left now is how to express the number of instances of a thread. Here are 3 examples of the exact same thread with the number of instances expressed in different ways. The first one, we have a number 632 UNC2B 0.18 deep thread 3 times. So there are 3 instances of this threaded feature. The next line is exactly the same thing, but the 3x appears before the thread specification. So it's read as 3 times 632 UNC2B 0.18 deep thread. And the third example, sometimes we abbreviate the word places as PLCS. This one is read as number 632 UNC2B thread 0.18 deep in 3 places. In summary, we now know that to fully define a threaded feature on an engineering drawing, we list the screw size or nominal diameter, we list the pitch, we list the thread form and the series along with the class fit, the depth or length of the threaded feature, and a symbol to go along with that, as well as the number of instances of that threaded feature. Great! That concludes our video tutorial on how to specify screw threads on engineering drawings based on the Unified Inch Screw Thread Standard. If you haven't already, be sure to sign up for free basic access to additional exclusive mechanical design and engineering content. Sign up at mechanicalengineeringacademy.com, where we have videos, courses, and certificate programs on the topics of product design and development, mechanism and machine design, automated systems, sensors and control, manufacturing fixture design, welded or fastener joint design, and much more. Additional exclusive content is being added on a weekly basis.